My name is Jing Li. I'm from University of California in San Diego. Today I'm going to talk about our work about the energy overhead of the mobile storage. This is a joint work with the researchers from Microsoft Corporation, and Stephen Swanson is my PhD advisor. So we are now living in the middle of the mobile era. So last year, over 1.2 billion mobile devices have been shipped worldwide, surpassing the total number of the desktop and the servers. One big difference between the mobile storage hardware and the storage hardware for the desktop or the servers is that they use low-end flash, like SD card or multimedia card, for three reasons. The first reason is that the energy overhead of those storage devices is pretty low compared with the SSD or HDD. And also the cost is pretty low. We can easily achieve less than $1 per gigabyte. And during the meantime, it can still deliver the adequate performance. For example, the eMMC 4.5 we tested, the sequential access can easily reach to 17 megabytes per second, and the random access can be up to 40 megabytes per second. And to deliver such performance, the peak power consumption is less than 250 milliwatts. That's pretty small compared with some commercialized SSD. And probably because of that, the conventional wisdom holds that storage system is not energy intensive. However, during this presentation, I will argue that is a mistake. That is a long-standing mistake. We concede storage device overhead is pretty low. It's just less than 1 microjoule per kilobyte. However, the storage stack overhead is high. Storage device is only part of the storage stack. The device overhead is low, but it doesn't mean that the storage stack overhead is also low. If you take in consideration about CPU memory need to coordinate to support the I/O operations. So look at these two guys. So the left one is a power breakdown of the normal usage stage from Surface RT. It's a mobile devices from Microsoft. And also we can see the change of the power if we issue an I/O request. So we can see that the majority of the increment of the power is from the memory and is from the CPU. The power of the storage hardware, the storage device, is only a very small part of the whole power from the storage stack. That means storage could affect the behavior of other energy-intensive components. I use the tip of the iceberg as an analogy for the people's misunderstanding of how much energy the whole storage stack may take. So most of people usually notice it's just the tip of the iceberg. The storage hardware is very energy efficient, but what most of people ignore is that there could be a massive iceberg below the surface of the water. So in this presentation, I'm going to answer three questions. So the first question is, how much is that? How much the rest of the storage stack need to take to support the I/O operations? And the second question is, considering that is very huge, so what's going on inside there? Who is eating my power? So I'm going to give a breakdown of the energy consumption inside the storage stack. And the last question I'm going to answer is if there's any ways that we can do to reduce the total energy consumption of the storage stack. And this is the outline of the rest of the presentation. So I'll first give a detailed analysis of the storage energy consumption. After that, I'm going to identify the major energy-intensive components. The last part of the presentation, I'm going to discuss the strategies to reduce the mobile storage energy. Okay, so part one, analysis of storage energy consumption. So first, a brief introduction to the experiment setup. So we want to draw some general or platform-independent conclusions. So we pick up two typical mobile devices. The first one is Samsung Galaxy Nexus S. The operating system running on that is Android 4.2. So we instrument the battery lead on that, and we connect to the Monson power meter, and through some software, we can monitor the power consumption inside the mobile devices. And the second device we're using is Surface RT from Microsoft, and the operating system running on that is Windows RT 8. We have collaboration with the Windows performance team and with the devices or instruments that we can have the power number of individual rails. We have a fine-grained power consumption breakdown. We have the power number for CPU, GPU, memory or storage hardware, and things like that. And also a brief introduction to the benchmark we are using. So we use both the macro benchmark and real application benchmarks. So micro benchmark is some simple I/O request, but we have some parameters to vary it during the experiment. The parameters include request size, access pattern. We have different cache configuration, and we use different write policy, write through or write back. We also compare the impact of using different programming languages, the impact of using different encryption configurations. And apart from the micro benchmark, we also have some real application benchmarks. So we are focusing on storage-intensive applications that still runs when the screen is off. The reason why we made such a choice is when the screen is on, the display component is the most energy-intensive components. But we are not interested in that, so that can be a very big or huge noise for our experiment. By the way, to reduce the noises, we remove those unnecessary applications from the mobile devices, and we turn off the hardware whenever possible. Say if we don't use the Wi-Fi or if we don't use the display things, that we will just disable it. For all the experiments, the idle power of the component is subtracted. The application benchmarks we're using includes emails, file synchronization between the client and cloud, application update, music player, and some messaging applications. All right, so let's see some results. So first is the energy spent on the storage hardware. So this is the result from eMMC 4.5, which is used by Surface RT. So the x-axis from this graph that we have different access pattern or different operations. So we have R&D and ICQ stand for random or sequential. We have RD and WR means for read and write. The y-axis is the energy per kilobyte in the unit of microjoule. So as you can see from this figure, that device requires only 0.1 to 1.3 microjoule per kilobyte for its operations. So just please remember this number because we are going to compare the energy of the storage hardware with the energy consumption of the whole storage stack. So, and you will see a very big difference. All right, so this figure is the energy, the overall stack energy overhead. I hope you guys still remember the number I provided in the previous slides, but in case you don't, I also put the number here. So the device energy is only for 8 kilobytes. So this graph is the result from the 8 kilobyte I/O operations. So the device energy is only 0.6 microjoule per kilobyte. But just look at the energy consumption here. So notice that the y-axis is in log scaled. So we notice that for the mobile devices, the whole energy consumption of the storage stack is from 100 to over 1,000 microjoule per kilobyte. That is 2 to 3 orders of magnitude higher compared with the device energy. At first, when we get this result, we are very surprised. So we kind of don't believe in that. So we begin to wonder if that has something to do with we are using the micro benchmarks. So we So we repeat the experiments for some real applications. So here is the breakdown of the real application energies. So we only, so this is only for the pure I/O operations. So as we can see that from this breakdown, at the bottom of each stack, each bar, that there's a very tiny blue stacks there that you can barely see anything there. So I use a red circle on that. So that is the energy of eMMC. So that is the storage hardware. That is just less than 1% of the whole energy. And above that is the CPU energy. That is about like half of the whole energy. And even after that, above that is the core energy, and even above is the memory energy. So from this, the result from the real application benchmarks, we can also see that the storage stack consumes 200 times more energy compared with the eMMC device. So we are really curious what is going on inside the storage stack, why the whole storage stack takes so much more energy compared with the hardware energy. So we have a breakdown of functionalities in these slides. We replace I/O traces and using some profiling tools. So we know like which API is running during the process and how much time each API is using. And then we classify them into 4 different categories. The first one is the file system APIs. And the second one is virtual machine APIs. Because the applications on the mobile devices, they are running on top of the virtual machine, so there could be a considerable amount of virtual machine APIs. So after that, we have encryption APIs. And the last part is some just the other APIs, we mean the benchmark logic APIs that has nothing to do with the storage system. So as we can see from this breakdown, by the way, this breakdown is with respect to CPU busy time. As you can see from this breakdown, most of the CPU time is spent on the encryption APIs. And after that is the virtual machine APIs. So even though the CPU busy time is not equivalent to the energy consumption, but it is still a very good indicator. So in the following part that I'm going to talk about the major energy intensive components, as probably you have already guessed, that is the encryption overhead and the runtime overhead. But before we go to any like experiment result or figures or tables or data, let's first take a look at why we need encryption. So that has something to do with the vulnerability of the mobile devices. The mobile devices can be easily stolen, can be easily robbed, and as compared with the laptop, the mobile devices is smaller, so it can also be easily lost. So if you don't have a mechanism to protect your data, you will suffer from a personal private data leakage. That's the reason why you need encryption. So even though there are some components inside some application-specific components inside the mobile devices that can help you to deal with encryption, the throughput of those crypto components are too low to meet the requirement of the storage system. And because of that, the designers of the storage system still decide to use the general purpose CPU to perform the encryption tasks. And because of that, so it adds a huge energy burden on the storage stack. So we designed an experiment to decide how much is the encryption cost. So we have 2 identical smartphones. The only difference between them is one is encrypted, one is not. And we run the same benchmark or applications on that, and we provide the result here. The y-axis here is the ratio of energy consumed by encrypted device over unencrypted device. So as we can see from here, so the encryption cost for RT or for Android is 2 to 6 times more energy. So that is very huge. And this is only the result for the micro benchmark. We also have the real benchmark result. So we use the, it's called Android bench. It is a representative storage benchmark on Android. It consists of some micro benchmarks, some real benchmarks like SQLite or some other applications you can see from here, like browser or any other things. So we use two Android phones. One is encrypted, one is not. And we run the same benchmark, and we can see a big difference here. So for the encrypted device, that it takes 31% of the whole battery life to complete the benchmark. And the number for the unencrypted device is only 1.3. So that means that there is a 2.5 times difference between the encrypted device and an encrypted device. All right, so we have talked a lot about the encryption things. Let's move on to the second one, like virtual machine overhead. So why do we need a virtual machine? Why do we need those runtime costs? So that has something to do with the isolation between applications. So on your smartphones, that you have some, sensitive data like passwords. You have some very valuable informations like geographic information, and more importantly, you have some financial information on that. So you don't want, say, like an application has the access to the sensitive data if they are not authorized to. And you also want to protect against the attacks from the malicious applications. So that's the reason you really need the isolation between applications. So the programmers use a managed language like Java or C# to achieve the goal of isolation. If you are written programs using Java or C# or some other managed language on Windows platform, that each applications that you wrote will be running on the top of the virtual machine, and the virtual machine will take over the isolation things. So even though such a mechanism makes it easier for the developers to build the applications and make the system more secure, it affects both the performance and the energy consumption. So let's see this experiment. So we designed an experiment to investigate the impact of using managed languages. So we first wrote a program using the managed languages, wrote the benchmark using the managed languages. That is the Java for Android platform and C# for Windows platforms. And after that, we have a counterpart written in the native language like C and C++, and we are also using the native APIs. So the y-axis in this graph is how much more energy you need to pay if you choose to use the managed languages over the native APIs. So as we can see from this figure, the impact of managed program languages is up to about 20 more energy for Surface RT, and for the Android, such number can be up to over 100. So that is also a very big number. So we have talked a lot about like how much energy the storage stack may take, and who are the major energy intensive components. So the last part of this talk, I'm going to discuss some possible ways to reduce the mobile storage energy. So we have a storage stack here. On the bottom of the stack is the storage hardware. And on the top of that, we have SoCs, we have encryption, we have file system, we have the virtual machine things. And during the rest of the talk, I will go through one level to another to discuss if there's anything we can do to reduce the energy consumption of the storage stack. So let's first take a look at the runtime cost. So currently, isolation is provided by software virtualization. We use managed language, we use pre-application users and groups, and we also use the virtual machines. But what if we can move in the storage virtualization into the storage hardware? That means that each application has an illusion of a private file system. And because they have a private file system, that they can use the native I/O APIs to deal with I/O requests. And the hardware will help you to take over of all the isolation things. And as we discussed from some previous slides, that if you use native API, that you can significantly reduce the power consumption of the storage stack. And we also noticed that there are a bunch of research projects that benefit from moving software functionality down to the hardware. Smart SSD from Swanson, it pushed down the database operators down to the hardware. And MonetaD and Mars from UCSD, they push down the protection or logging system down to the hardware, and by pushing down the software functionalities down to the hardware, they achieved great success in terms of performance. So we are looking forward to some possibilities of moving storage virtualization into the storage hardware. And let's move to the second level, file system. So if the encryption hardware doesn't improve, the throughput of encryptor cannot be high enough to meet the requirement of the storage system. So we need to still using the general CPU, general purpose CPU to deal with the encryption tasks. So we need to rethink about the policy, the encryption policy inside the file system. So currently, we are using the what we call all or nothing policy. So that means that you can either choose to disable the encryption or you need to turn on the full disk encryption. However, sometimes it can be an overkill. There are some components that you can never benefit from encryption, say operating system libraries, or most pre-installed application binaries that you cannot benefit from encryption for these things because they appeared on everyone's phone. There's nothing private here. So we are thinking about you can think about the file system that you can specify something you can go to encrypt and something that you don't need to encrypt. So a naive solution is that you can specify two partitions on your file system. So the first one is for the encrypted data, and the second one is for unencrypted data. So, but there's a big problem with that. So because that you need to specify the size of each partitions when you format the device, and after that you cannot dynamically change. So we are exploring the possibilities of using the partially encrypted file system. So Linux has the GNU Privacy Guard, and Windows have the encrypting file systems. So that is a file system that you can choose to encrypt the data, only those sensitive and private data. And that means that you can dynamically change the size of encrypted part and unencrypted part. So we are really looking forward to some similar file systems for the mobile devices because it can significantly reduce the energy consumption of the storage stack. All right, the last solution has something to do with the SoCs. So dealing with the power issue is not a new problem. So researchers have been going for a few decades to deal with the power issue of mobile devices or embedded system device. So DVFS and ASIC is the two major approaches. So the idea of the DVFS or dynamic voltage and frequency scaling is that you can dynamically adjust the voltage or frequency based on the offload or utilization of the system. But we are more interested in the ASIC, the application-specific integrated circuit. Instead of building some general purpose components, we can also choose to build some application-specific components. And because we are not building the general purpose things anymore, that we can take advantage of using some application-specific optimizations in terms of both the performance and the energy consumption. We noticed that there are a few dedicated ASIC on mobile devices, like we have dedicated ASIC for decompression, we have dedicated ASIC for DSP. So we are also looking forward to some possibilities to do the SoC offload engines for storage operations. It can either support encryption or it can help to support the storage hardware virtualization. All right, so that's all about the content of the presentation. So just a brief conclusion. So we first illustrate that storage stack is energy intensive. The device energy is low, but the rest of the stack is not. And after that, we identify the major energy intensive components. One is the encryption mechanism, the other is the runtime environment. And there are more details more data, statistics in the paper. So if you're interested, read that or talk to me offline or ask questions. So I'm ready to take questions now. Thank you.
This is Yang from UC Santa Cruz. So I'm just wondering, how did you measure the energy impact of storage stack on DRAM? So actually, as I mentioned in the slides there, do you mean how we measure the power consumption of the DRAM? The energy overhead. I know how did you measure the energy impact, the energy consumption of DRAM, but how did you attribute which part to storage stack and some of them to other parts of the system?
Oh, okay, I got the point. So actually, for example, for the application benchmarks, we first run the application and we collect the I/O trace, and then we replace the I/O trace. So that is the cost of the storage. So we only replace the I/O trace. We don't report.
So the energy that you showed in the bar chart that attributes to DRAM are actually all the energy consumed by the DRAM during that benchmark period, right?
The idle power has been subtracted,
okay.
And also we are just replaying the I/O trace. So.
Okay, got it. Thanks.
Hi, Mohammed Khatib, HGST. Actually, slightly tangential questions here. For the energy when you are measuring it, so for the CPU as well as for the DRAM, if you are not operating any workload on them, they will be still consuming some energy while being idle, right? For the DRAM to refresh for the CPU, unless you use some clock gating or something, which I think you are not. So now when you are applying a workload, how do you basically separate a basic static energy from the dynamic energy, which is really pertaining to what you are doing in terms of I/O operations?
So do you mean there's some idle power?
So let me give this scenario. Suppose you are doing nothing on your iPod, it's gonna still use some energy for the DRAM to refresh, unless the DRAM is a mobile, intelligent, smart DRAM. Mm-hmm. Now the same thing for the CPU, unless it has some clock gating and some other features. Mm-hmm. Now, if you decide another scenario, instead of like having it idle, you play music. Now there is basic energy which is gonna consume anyways, regardless of what you are doing. Mm-hmm. And now if you are streaming or doing MP3, it's gonna use the CPU to decode and maybe to do this I/O operation to execute the software stack. At the same time for the DRAM to read in the bits and read out the bits to the CPU. So now the question is how you are separating the energy due to the bits related to the streaming, to the music, and just the static energy that's unrelated to this operation.
Okay, so the result in the experiment is from replaying the I/O storage trace. So we only focus on the storage-related things. So if this trace that is not related to the I/O or storage things, that we are not going to replay them.
Okay. I think that's all the time we have for questions. Let's thank Jing.
Okay.